Good morning. Welcome back. Only announcement is just a reminder that the Unit Exam 2 is in class on Friday. You don't need a Scantron. You'll be able to write on the exam packet. Just make sure you have something to write with and a non-graphing calculator. You'll be provided the same periodic table and equation sheet and some scrap paper. So that's all that you will need. All right, so we are continuing our 16.2 notes. Let's just look back and remember what we did last Friday. So we talked about strong acids and bases and a little bit about weak acids and bases. The last slide that we discussed was about bases. Remember that bases increase OH minus concentration in solution. And so strong bases are sources of the OH minus. I'm gonna have to get like a laser pointer. That'll be a lot better. But strong bases are sources of that OH minus ion. So potassium hydroxide, barium hydroxide. They are on our list of strong bases. Other molecules that act as bases are not a source of the OH. Like there is no OH ion in this molecule. But when it's added to water, it will take a hydrogen from water, and the water becomes OH minus, some of the water, right? This is a reversible reaction, so what's on the right and left is present in solution, but a weak base increases OH minus ion concentration by reacting with the water molecule. And then acids increase the H plus concentration. I won't go back to that slide, but that's what we talked about on Friday. So this section now we're going to talk about Bronsted-Lowry theory. We briefly discussed the Bronsted-Lowry definitions of acids, which is that it is a source of protons or H plus ion. So we'll just continue talking about these acid-base reactions. So again, there are a few different ways to define acids. This is a very common way. You'll see this when you go to organic chemistry as well. There we go. Okay. So acids are the proton donors. Remember, a proton is a hydrogen without an electron, so H plus. So acids are capable of releasing an H plus in solution or giving an H plus to the base or giving it to water. Bases are proton acceptors. So we have an acid that gives away a proton, a base accepts that proton. These are capable of creating a new bond to the H plus. So with this reaction that's shown here, take a minute to identify the acid and the base in the forward reaction. So which molecule there is giving up a proton, that will be the acid, and which molecule is accepting a proton, that will be the base. Okay, so we're looking at really what's different between the reactants and the products. Let's start with the first molecule here, C2H3O2. The most similar molecule to this on the right side is the last molecule here, the anion. And the difference between these two is that there's one less hydrogen over here, and it gained a negative charge. So that means that this molecule gave up an H+. So it was the proton donor. So that is the acid. If we look at the other reactant, H2O, most similar molecule to it in the product side is H3O+. The difference between these two is going from reactant to product. H2O gained a hydrogen and a +1 charge. That means it gained a proton, an H+. The molecule that gains the proton, looking above to our definition, the proton acceptor, that is the base. So we're looking at really the difference between having a proton or not, between the reactant and the product side. Now you might notice that in this reaction, water is the base. In this reaction from Friday, water was the acid. It gave away a hydrogen, so water acted as the acid in the solution. Water can act as both an acid or a base. So if something is added to solution, it depends on if that molecule that's added to water is more acidic or less acidic than water. And that will tell you water can act as an acid or a base to complement the molecule that's added. So an underlying assumption of this theory is that there's always an acid, so always a proton donor present, and always a base, always a proton acceptor present. So if there's not a specific compound added to solution to act as the acid or the base, then the solution molecule, which is often water, can serve that role as the acid or a base. So water can act as a Bronsted acid and a Bronsted base. You would either be able to tell by looking at reactants and products if water is acid or base, or you'll be told that you're adding an acid to solution. If you're adding an acid, then water will act as a base to complement the acid. Or if you're told a base is added to solution, then water will act as an acid so that the other molecule can act as a base. There'll always be an acid and a base present. So if one is not specified, water will fulfill the missing role. Now, another important piece of Bronsted-Lowry theory when we're talking about reversible reactions is that the reverse reaction, so going from products to starting material, is also an acid-base reaction. On the right side, again, if you're looking at the reverse reaction, we have an acid and a base. So look at this reaction for a moment here. Imagine the reverse reaction, so starting with H3O+ and C2H3O2- and forming the reactant. So reaction in reverse, label of the acid on the right side and the base on the right side. So which one's giving away a proton, which one's donating a proton. Again, for the reverse reaction now. Okay, let's start with H3O+. So we're determining for the reverse reaction, is H3O+ the acid or the base? Does it give away a proton or does it accept a proton? If we compare H3O+ and then the most similar molecule on the left, H3O+ for the reverse reaction becomes H2O, which means that H3O+ in the reverse reaction gives away a hydrogen with the +1 charge, a proton. So H3O plus gives away a proton. It is the acid for the reverse reaction. The term for the acid for the reverse reaction is conjugate acid. That must make the anion the conjugate base, but let's double check. Looking at the reverse reaction, starting with the anion, the difference between this one and the most similar molecule on the left side is that through the reverse reaction, the anion gains an H+. Gaining an H+ means that it is the base. So this is the conjugate base. We already identified the first molecule as the acid and water as the base. So every balanced Bronsted-Lowry reaction will have an acid and a base on the left side and a conjugate acid and a conjugate base on the right side. Conjugates are always on the right, and they're just, that word conjugate is there to explain that for the reverse reaction, that conjugate acid is the acid, or for the reverse reaction, the conjugate base would act as the base. So conjugates always on the right side, acid base always on the left. And then pair of molecules that differ only by one H+. Those are the pairs that we're comparing to determine if something is an acid or a base. These are called a conjugate pair. And then an example here is H2O and H3O+. They differ by one H+. H3O+ has the extra H+. H2O does not have it. For conjugate pairs, one is the acid for that reaction and one is the base. And then one of them is the conjugate. So in this example, H2O is the base. Well, then H3O+ is the conjugate acid. The first molecule is the acid. The last one is the conjugate base. So they are a conjugate pair. One's an acid, one's a base. Okay, so on this slide now, I have the reaction from the previous slide. We have acid base, and let's add in that H3O+ is the conjugate acid, and the last one is the conjugate base. We're just missing that conjugate part. And then H2O and H3O+ are a conjugate pair. The first and last molecules are conjugate pairs. So with that in mind, look at this reaction, identify acid base, conjugate base, and connect the conjugate pairs. I'll give you all some time to work on that. Okay, let's go through this reaction here. So if we start with the first molecule, NH3, and then look for the molecule on the product side that differs by 1 H+, that's NH4+. So by identifying this conjugate pair, we can see for that conjugate pair what happens in the reaction for that reactant. NH3 becomes NH4+. That means that NH3 gained a proton, gained an H+. So NH3 is the molecule that gained the H+. That is the definition of a Bronsted base. Bases gain H+, acids donate H+. So NH3 is the base. Then that makes NH4+ the conjugate acid. And then these two are a conjugate pair. That should make H2O the acid, OH minus the conjugate base, but let's double check. So H2O, its conjugate pair is OH minus. In this reaction, H2O loses a proton and becomes OH minus, or it donates a proton to the base. It gives away a proton. That's the definition of an acid. So H2O is the acid. OH minus is then the conjugate base, and these two are a conjugate pair. Conjugate pairs, like I said, one will always be an acid, one will be a base, but you can double check and consider the reverse reaction. NH4+ becomes NH3. That means for the reverse reaction, NH4+ gives away a proton. So that means NH4+ is the acid. It's on the right side, so that makes it the conjugate acid. And then we can do the same thing for OH minus. Okay, questions so far on conjugates or identifying acid base? Yeah.
So you only have a conjugate because it's an equilibrium, right? Like if
Yeah.
reaction would have it.
I don't think we identify conjugates for irreversible reactions. You could though, you could. Because even if it's an acid breaking, I'm gonna say we won't do that in our class. Yeah. So in this reaction, it's giving away a proton, a hydrogen, and becoming OH minus. So in this reaction, it's an acid. And what's happening is we have this NH3 molecule present, which is more basic than water. So it causes an acid-base reaction where the NH3 acts as the base and the OH acts as the H2O acts as the acid. So we'll very soon talk about how water can act as both an acid and a base, and even between two water molecules, we can have an acid-base reaction. But that's the next section. We have like 2 slides before we get there. Other questions right now? Okay. So we see here each base, or the bases have a conjugate acid, acids have a conjugate base. The strength of the acid or base provides information of the strength of the conjugates. So here's the trend. For acids first, a strong acid will produce a weak conjugate base. A weak acid will produce a strong conjugate base. Strong bases produce weak conjugate acids. Weak bases produce strong conjugate acids. We're talking about acid and base strength on a continuum. Even between weaker acids, we can have stronger and weak acids. Even if they're not part of the strong acid list, there's a big range of how strong an acid is. So the stronger acid will produce the weaker conjugate bases, and stronger bases produce weaker conjugate acids. Again, acid and base on the left side, conjugate base and conjugate acid on the right side of the equation. So with all of that in mind, spend some time working on this question. we have 3 acids listed in order of acid strength. The left is the strongest acid of this list. So again, these are all not on our strong acid list, but they are not the 9 strong acids we have in our notes. They're under the umbrella of weak acids, but HClO is still stronger than HBRO, which is still stronger than HIO. So this is weakest acid. So you're provided the list of strong to weak acid for these 3 acids. Identify conjugate bases. So do that first. Remember that if something is an acid and has a conjugate base, it loses a proton. It loses an H+. And that should tell you a little bit about what the conjugate base structure would be. So identify the conjugate bases and then list them in order of base strength from strongest to weakest, keeping in mind what we just said on that last slide. So first identify conjugate bases and then organize them. When you're drawing out conjugate bases, don't forget the charge that base might have. Losing an H+. Okay, let's draw these conjugate bases. And I wrote this note across the top. Remember that acids donate a proton. So if we look at HClO first, so chlorine, hydrogen, chlorine, and oxygen, that will donate a proton. So let's just say in a reaction, it gives away a proton to the base. Then what's left? Well, if it lost an H+, then we still have ClO-. It separates into H+ and ClO-. The H+ will be picked up by whatever base is present, and then the ClO- is the conjugate base. We balance out the charge, so if it's neutral first and it loses an H+, then we have a ClO- left over. So conjugate base for HClO is ClO-. Conjugate base for HBRO, BRO-. conjugate base for HIO, IO minus. So those are the structures of the conjugate bases. Again, just the molecule without an H plus. Then we're looking to list from strongest to weakest bases for those three conjugate bases. We have to go back to what we have on the last slide, that if you have a stronger acid, that will produce a weak conjugate base. A weak acid produces a strong conjugate base. So they're opposites. So the strongest acid here, HClO, the conjugate base will be the weakest base. We have HBRO in the middle, so BRO minus will be kind of between as far as base strength, and then IO minus will be the strongest base. So we're flipping the order. Weaker acid, stronger base. Stronger acid, weaker base. Questions on this one? Okay, so this is the end of what will be on the assessment, up to 16.2. 16.3, we're going to start. We're going to continue chapter 16 on Wednesday, but at this time you have everything you need to study for the assessment. So this next section is about the auto-ionization of water, which is essentially water itself becoming ions without anything else present. So remember we saw acid-base reaction. Well, we saw multiple acid-base reactions with water. Sometimes water is an acid, sometimes water is a base, and I said it depends on what else is present in solution. If all that's present is pure H2O, it can still act as a base and as an acid. So in the same reaction with just H2O, our acid and our base are both H2O. One of the water molecules can donate a hydrogen and the other one can accept a hydrogen. And we form H3O plus and OH minus. So this particle picture, we have two H2O molecules. One of them gains a hydrogen. This is H3O plus. One of them lost a hydrogen. This is OH minus. Now this reaction lies far to the left. We have pure water in a beaker. Most of that is going to be neutral water, but some of it is H3O plus and OH minus, and this ends up being really helpful for calculating concentrations of H3O plus and OH minus in solution. So for water, let's see. I already said everything at the top. The reaction proceeds to the right a tiny extent. Because water is both a weak acid and a weak base. The equilibrium constant for this expression, or for this reaction, this is Kw, the same K that we've worked with, the W for water. So it's the K for water. It is reactants over products, products over reactants. The products are these ions, H3O plus and OH minus. Reactants are H2O liquid. So we don't include that in the K expression because it's a pure liquid. So K expression, H3O plus concentration times OH minus concentration at 25 degrees Celsius for pure water without any acid or base present, it's always 1 times 10 to the negative 14. So this value will become really useful when we are doing future calculations. So equilibrium constant for this reaction, this is sometimes called the water ionization constant. Kw. At a pure water without any acid or base present, H3O plus will equal OH minus concentration, and they will be 1 times 10 to the negative 7, both of them. You multiply that together, you get 1 times 10 to the negative 14. So if H3O plus concentration equals OH minus concentration, we say that it is a neutral solution. we have equal amount of H3O plus and OH minus. Now, because this value will always be equal to H3O plus concentration times OH minus concentration, those two concentrations are inversely proportional. If you increase H3O plus concentration, then OH minus concentration has to decrease. Or if you increase OH minus concentration, H3O plus concentration has to decrease. Because the product of the two always equals 1 times 10 to the negative 14 at 25 degrees Celsius. Okay, so with that in mind, let's do these calculations. We have two aqueous solutions at 25 degrees Celsius. Each one has different concentrations of H3O plus. So given the concentrations present here, so first one, 4.68 times 10 to the negative 11, that's different than 1.0 times 10 to the negative 7, right? So we have a lower concentration of H3O plus. That means OH minus concentration will differ. So using the equation on the previous slide, this one here, calculate the OH minus concentration in these two solutions. If you're not sure where to start, take a look at that equation at the top here. The KW value is given. That will be, well, you don't need it for this exam, but for future exams, that's on the equation sheet. 1.0 times 10 to the negative 14. You also have H3O plus concentration for that solution. So you just need to solve for OH minus concentration. So just remember that acids increase H plus concentration or increase H3O plus. We use those interchangeably. Bases increase OH minus. So if there's an increase or a higher concentration of OH minus, it would be basic. With higher concentration of H plus, then it would be basic.
Okay, compared to the
Yes.
Okay, thank you.
Or you can compare it to the 1 times 10 to the negative 7 for a neutral solution. Either one.
the OH side. Oh, let's equal the same thing.
Okay, let's do some calculations here. So I just rearranged that equation at the top. Concentration of OH minus is equal to that Kw value divided by concentration of H3O plus. And I just rearranged that first equation to get that. Kw 1.0 times 10 to the negative 14. Concentration of 4.68 times 10 to the negative 11. It's provided in the question. So the concentration of OH minus is what that fraction is equal to, which is 0.00021 or 2.1 times 10 to the negative 4. Then let's do the same thing for the second solution, and then we'll discuss if these solutions are acidic, basic, or neutral. So same thing, concentration of OH minus for solution 2 is Kw divided by concentration of H3O plus. We have a different concentration of H3O plus here. So we plug that in. OH minus concentration, 3.17 times 10 to the negative 12. Okay, so just plugging in values and solving here. Now the question is solution 1 acidic, basic, or neutral? Is solution 2 acidic, basic, or neutral? So let's remember that acids increase H plus concentration. And we also say H plus is interchangeable with H3O plus. So if you add H plus to water, then you get H3O plus. So acids increase H3O plus concentration. Bases increase OH minus concentration. You can make an acidic solution by adding acid to it. When you add acid, like HCl, the H3O plus concentration increases. A neutral solution would be when concentrations are equal, H3O plus and OH minus, and they're both 1.0 times 10 to the negative 7. But if we have a basic solution, then the H3O plus concentration will be higher than 1.0 times 10 to the negative 7. And in an acidic solution, the OH minus concentration will be lower. So if we increase H3O plus, we have to decrease OH minus. And then for a basic solution, OH minus concentration will be high, H3O plus concentration will be low. So the first solution here, H3O plus concentration is 4.68 times 10 to the negative 11. OH minus concentration is 2.1 times 10 to the negative 4. So the OH minus concentration is higher than the H3O plus concentration. OH minus, basic. Higher OH minus means basic solution. So this is a basic solution. Because the concentration of OH minus is higher than the concentration of H3O plus. The second solution, the concentration of H3O plus is higher than the concentration of OH minus. We're looking at 10 to the negative 12 versus 10 to the negative 3. 10 to the negative 3 is a larger value. So H3O plus concentration is higher, which means acidic solution. So Solution 2, acidic because concentration of H3O plus is greater than OH minus. Any questions about this problem or these? Yeah.
What would the value need to be for it to be neutral?
The value for it to be neutral would be they both have to be equal, and for them to be equal and kW to fulfill that it has to be 1.0 times 10 to the negative 14, then they are 1.0 times 10 to the negative 7 each. So that will be a neutral solution. So you could also always compare to this. If OH is higher than this, then it's basic. If H3O plus is higher than this, then it's acidic. Okay, so we can calculate H3O plus and OH minus concentrations to determine if a solution is acidic or basic, but knowing whether a solution is acidic or basic is very useful in the lab. It's very useful in industry. Like, this is used in a lot of different scenarios, and having to calculate these really small numbers, these are kind of difficult to work with. We often have to use scientific notation. And so the pH scale and pH calculations, which is our next unit, are a useful way of taking those really small numbers and making them more manageable for actually using this in the lab. So the pH scale, while H3O plus and OH minus concentrations, we're talking about concentrations here. Most common concentration unit is molarity. Remember, this is moles per liter. So for a weak acid, those concentrations, the amount of moles of that H3O plus or OH minus is usually really small for a lot of liquid. So we have very, very small concentration values. So instead of using those really small concentration values, we use the pH scale, which has values between 1 and 14. So nothing less than 1, nothing greater than 14, and they're often just with a few decimal places, but it's a much easier way of comparing acidity or basicity of a solution. So the equation for pH, make sure you have this down. We take the negative log of the concentration of H plus, or we can say negative log of the concentration of H3O plus, because H plus and H3O plus are interchangeable for us. So the log is a function in your calculator. So if you know the concentration of H3O plus, you take the log of that and then change the sign. Log is base 10. So if you take the negative log, or let's just say the log of this value, we have 1 times 10 to this exponent. The log, which is base 10, essentially removes the 10 here. And if you just took the log of this number, you'd get the values negative 7. But we take the negative log, which would make the value positive 7. So pH for neutral water, where H3O plus concentration is 1 times 10 to the negative 7, we would take negative log of 1.0 times 10 to the negative 7. If you plug that into your calculator, you will get the value 7. So with that in mind, let's go to the two solutions that we calculated the OH minus concentrations for on the next slide. Same two solutions from the previous problems, and calculate the pH of those solutions. So we're just using this equation here, but with the H3O plus concentration that's provided. Okay, so first solution here, H3O plus concentration is really small, 10 to the negative 11. You take the negative log of that concentration, the pH is 10.3. For the second solution, with a higher concentration of H3O plus, the pH of this solution is 2.5. Now we determined when we calculated concentrations of OH minus that this first solution is basic. So the concentration of H3O plus was low, OH minus is high. And the second solution is acidic with a higher concentration of H3O plus. But notice that the pH for the basic solution is higher than 7, than neutral water. pH of the acidic solution is lower than 7. So more acidic solutions have lower pHs. Low pH, more acidic. High pH, more basic. So this next slide summarizes that trend. pH of 7 is a neutral solution. Less than 7, we call that acidic. Greater than 7 for the pH, we call that basic. And then here are some common solutions. Our stomach acid pH is between 1 and 2. Soft drinks are acidic at a pH of 3, vinegar 3, orange juice 3.5. Then human blood has a higher pH at 7.3, just above neutral. Seawater with lots of ions, salts in it is 8.5. Baking soda would be a solution with a pH of 8.5. So those are a few examples. Certainly ranges between 1 and 14. Questions on pH? Okay, for the iClicker today, we're going to do a little bit of a gear switch and go back to some old content. And the question today is on intermolecular forces. So hopefully some of that will come back to you. I have 4 questions with molecules asking about the intermolecular force for those molecules. So it's from chapter 12. If you need to pull up your chapter 12 notes, feel free to do that. But yeah, take a look at those. And try recalling intermolecular forces.
So it does.
And the jump. That jump
Yeah. Okay, I'll leave this open for a few more minutes, but before anyone packs up, keep in mind, well, you all know, we have our assessment on Friday. As you're studying, hopefully throughout the week, keep in mind that I have office hour tomorrow. It's a good time to ask questions. I will have an office hour on Thursday, another good time to ask questions. And we have our recitation Friday morning, another good time to ask questions. So, as questions arise, you can email me, but I these students find it more valuable to have a verbal explanation. So those are 3 times that we can do that. Tomorrow? 2 o'clock tomorrow. Yeah.
So for the assessment, this slide is where
Yes.
it starts. right?
Yeah.
So last time the equations were not included.
Right. So you won't have these equations. You're not going to need them. I'll be
Oh.
honest. This is on the equation sheet.
Okay.
Yeah. So that will be really where you should start. Is the
This-
2-point Arrhenius equation.
There won't be.
No.
Okay. Oh, it's the same thing, but this is like 2-point version.
Yeah.
of-
Exactly.
Okay, perfect.
Yeah.
Thank you.
You're welcome. Yeah. Oh yeah. So there'll be 18 multiple choice and then 2 short answers.
Okay. And then, what do you recommend best way to study for the test?
Yeah, so I think it's helpful to start with looking at the lecture notes, just like getting a refresher. So 14.4 through 16.2, which we covered today, just to like refresh the content that we covered, what's going to be on it. And then I recommend either like trying our learning checks again. If those you find like any of them confusing, try to work through them. And if they're still confusing, you can always go back to the recordings and hear it explained again. And then the achieve questions I think are also helpful that are relevant to the content in those sections.
And for the previous tests, like the midterm, I struggled particularly with the conceptual-based questions.
Okay.
What would you recommend is the best way to prepare for that?
So I do think there's a lot of conceptual questions on the like learning curves, the adaptive quizzes.
Okay.
So I think that can be helpful. Another option is the ACS book in the students or in the office. Have you looked at the ACS book at all?
No, I haven't.
Okay, so they have a mix of conceptual and math questions. You do have to purchase it. They have an old one that you can get, like they'll just give you for free. We can walk over there if you want to look at them real quick. But if
Sure.
okay,
Yeah.
let's just do that. And then, 1 second.